So no, I haven't even looked at the exams yet. I'm not sure when I'll be able to get to them. It might not be till this weekend because so many things. So let's get the house lights up. And let's turn these stupid can lights off. I hate those things. Can lights. Go away.
I don't know, it's so slow when I try to like scratch it off. Or, this is good. This is a box of nuts and bolts. I needed to get specialized screws put together my independent study. I wish they were here this morning, so when I had my meeting, I could have been like, get something together. But I was like, give me 3 hours. I don't know. There's a table in Hanwell that said free, and I saw snakes and ladders, so I just grabbed it.
Aha, yeah, I was like, what are you doing with snakes and ladders? I'm thinking like, yeah, okay.
I thought it'd be a fun game to play with.
Sure, why not? Yeah. I believe I'd certainly appreciate that. I love it when people are just like playing games while I'm talking. Yes, it makes me feel so good. Let's see. Okay. Stop it. Okay.
It's worse when I don't have fingernails. Oh, there's tape here, tape here, tape here. I hope there's not more. It's really hard.
You open it and it's just another container that's tape.
The whole thing is just tape.
Everything is tape. It's all tape.
Tape is a nail biter's worst nightmare.
Oh, no. Yeah, that does sound awful. Stop it. What are you doing? All right. Whatever. I'll just get this started here. Oh, now it's connected. Okay, thank you. Give me that mousey. Oh, whatever. Okay. And I want these lights on. Hooray. Okay, so I'll remind you that last time we were going aha-saha equation. So I'll write it out and then I'll immediately put up a slightly different version where we write it in terms of the electron pressure. So we said that the Saha equation looked like this. Ni plus 1 over Ni, number of atoms in ionization stage I plus 1, they've lost I plus 1 electrons, divided by the number in ionization stage I, they've lost I electrons, is a lot of stuff. 2 coming from electron spin, it turns out. Zi plus 1 over Ne, the number density of electrons, Zi. So those are the partition functions for stage I plus 1 and stage I that we talked about last time. Mass of the... Well, that's extremely sad that that happened. Ugh. Oh, no.
It happens to Dr. Trees a lot.
Does it really? It's what happens when you use this wonderful Hagoromo chalk that's a little bit softer. It writes nicely, and then it disintegrates, and how am I supposed to function now? You don't want me to write in orange, do you? Because that's harder to see, sort of, maybe, kind of. Is there any more here? What do you think of orange or yellow? Let's go.
There's some in advanced lab. I can grab it.
Is there? Let's see. Well, here's some yellow. I think this will work well enough for here. But I do appreciate it. I do appreciate it. I might even take you up on that offer. But for now, let's see if we make do with some yellow chalk here. Maybe it won't even crush as easily. I don't know.
Lots of chalks in there.
What's that?
There's a box of chocolate.
Oh, that's almost as good as a box of chocolate, but not quite as good. All right, yeah. I mean, if you're going to make me choose between chalk and chocolate, I will take the chocolate, but
Take the chalk.
you'll take the chalk. Okay, all right, well, please enjoy. Right? Yeah, okay. To each their own. MEKT over 2 pi h bar squared to the 3/2 power e to the minus chi sub I, the ionization energy for stage I, over kT. So remember that chi sub I is how much energy it takes to go from the ground state of stage I to the ground state of stage I plus 1. So that's going to show up in how hard it is to go from stage I to stage I plus 1. It exponentially decays with that ionization energy. And now we're just going to write this also in terms of the electron pressure. Sometimes we just decide to use that in terms of the electron pressure. And this is just the ideal gas law that I'm going to write here, right? In chemistry, you do PIV-NERT, right? PV is nRT. But in astronomy, we're typically going to use the ideal gas law in the form of number density times the Boltzmann constant times the temperature is another way to write the ideal gas law. So the electron pressure, P sub E, is the number density of electrons times the Boltzmann constant times the temperature. So notice that NE would be the number of electrons per unit volume, so to speak, right? So this is related, right? In other words, the volume is kind of hidden here. And so if you wanted to PIV-NERT it, you can kind of take the volume to the other side. But it's per unit volume, not the actual volume, et cetera, et cetera. But anyway, suffice it to say that this is really just another way of writing the ideal gas law, is what it comes down to. So, in terms of the electron pressure, well, we'll just then use the fact that NE is equal to PE over KT and just substitute that here. So Ni plus 1 over Ni in terms of the electron pressure just becomes 2KT Zi plus 1 over PE Zi, electron pressure Zi, times all the other stuff is the same. MEKT over 2 pi h bar squared, 3/2 power, raise that to e to the minus ki over kT. So these are entirely equivalent to one another, but we'll note that in a stellar atmosphere, typically 0.1 newtons per square meter is less than or equal to roughly the electron pressure is less than or equal to roughly about 100 newtons per square meter. Remember, pressure is force per unit area, so it has units of newtons per square meter. Anybody remember what you call, what's the fancy person's name word for a newton per square meter? Do you know? Starts with a P. Blaze. Pascal. The Pascal is the newton per square meter. What's atmospheric pressure on Earth, roughly speaking? Do you know that? Much more than 1 Pascal. It's about 100 kilopascals. It's about 100,000 newtons per square meter is atmospheric pressure. Put in terms of, you know, the much more reasonable American units, 14.7 pounds per square inch, roughly, is atmospheric pressure, which is quite a lot, right? The air, it's like 14, almost 15 pounds of pressure on every square inch. But you have an equivalent internal pressure, which is why you're not feeling crushed, essentially. You're pushing out just as hard as the air is pushing down on you. But that's also why not a good idea to suddenly drop the pressure. Bubbles of nitrogen will start coming out of your out of your blood. You'll get a terrible case of the bends, which can be fatal if you do it too quickly because those little nitrogen bubbles form, block blood vessels, and you die. Don't do that. That's why they have to slowly decompress divers. Anyway, point here is, so the electron pressure in the stellar atmosphere is actually a lot less than atmospheric pressure here on Earth, but that's typical values for just the electron pressure. What questions do you have? Shall we do an example? Yes, we shall. We shall do example 8.1.4 from the book. Let's follow in the footsteps of Cecilia Payne, Kapachkin. Example 8.1.4 from the text. Consider the degree of ionization in a stellar atmosphere composed for simplicity of pure hydrogen. None of that helium contamination that's there in a real star. None of those quote-unquote metals. It's going to be pure hydrogen. And that's not too bad an approximation, because about 9 out of every 10 nuclei in a stellar atmosphere is hydrogen to begin with. So consider the degree of ionization in a stellar atmosphere composed of pure hydrogen. I'm discovering that the yellow chalk, Hagoromo though it may be, seems to be more sturdy than the white chalk, as a matter of fact, which of course is what I say just before this one crushes itself too. But nevertheless, I've really asked for it there. It's stupid. Consider the degree of ionization in a stellar atmosphere composed of pure hydrogen. Pure, delicious hydrogen right there. Assume for simplicity that the electron pressure is constant and equal to 20 newtons per square meter, because that's an approximation, because if you ionize the hydrogen, you're making electrons, which is going to change the electron pressure. Complicates things. Let's not complicate things. We get most of the physics by keeping it simpler. So, assume for simplicity that the electron pressure is constant, namely P sub E is equal to 20 newtons per square meter. And what we're going to want to find is the number of ionized hydrogen divided by the total number of hydrogen atoms. We want that fraction. So rather than just Ni plus 1 over Ni, or in the case of hydrogen, because we're astronomers, so let's see. So what are the ionization stages of hydrogen? It could be neutral, right? So that would be I is equal to what? Little I is equal to what for neutral hydrogen? 1. No. Because I is the number of electrons, little I is the number of electrons that have been removed. Ionization stage I is the atom with I electrons removed. So neutral hydrogen, how many electrons have been removed so far if it's neutral? 0. So that's I equals 0. But what Roman numeral should we use to represent that? 1, because the Roman numeral is 1 more than the number of electrons that have been removed, because we're astronomers, damn it. And then let's see, ionization stage 1 electron has been removed. That's Roman numeral 2. Are there any other ionization stages for hydrogen? No, because there's only 1 electron to get rid of. So we want to find N2, the number of ionized hydrogens, divided by and total, all the hydrogen nuclei. So how many have been ionized? How many are just bare protons? divided by the total number of protons attached or not attached to an electron around. Well, that'll be N2 over, for hydrogen, N total is just the number that aren't ionized plus the number that are ionized. With another species, you'd have to add all the ionization stages available. So for example, if we're talking helium, that would be N1 plus N2 plus N3, because helium can lose 2 electrons. But for hydrogen, it's just N1 plus N2, neutral hydrogen plus ionized hydrogen is all the hydrogen. But wait, the Saha equation doesn't tell us that, but we can do the same trick we did before with the Boltzmann equation and express it in terms of something that the Saha equation does tell us, namely N2 over N1, right? That's the Boltzmann equation, the Saha equation tells us ionization stage I plus 1 over ionization stage I. So here it can tell us N2 over N1, the number of ionized hydrogen divided by the number of not at all ionized hydrogen. By the way, have you ever noticed before that there are 2 pronunciations of this word that mean very different things, right? In other words, you could have unionized laborers or unionized atoms. So that's a pretty good example of one of those kind of situations like that there. So we're not talking about hydrogen that doesn't belong to a union or anything like that. So N2 over N1 plus N2, just divide through by N1. N2 over N1 divided by 1 plus N2 over N1. Just divide the numerator and the denominator by N1, and that'll give us what we want, because the Saha equation does tell us N2 over N1. And so we can get N2 over N total by just having 2 copies of N2 over N1 in our expression. Now, to write that out, right, 2 copies of the Saha equation, but you can do it. Mathematica doesn't care. Why? You can use Mathematica in joyfully doing a homework problem that'll be similar to this. I know, you can't wait. I can't wait either. So we want to find that, and we're just going to say, as a function of temperature for 5,000 Kelvin is less than T is less than 25,000 Kelvin. Let's say. That's what the example does. Let's look in that range. 5,000 is less than T is less than 25,000 Kelvin. So again, in the end, we're just going to say, here's the plot, because the way you do this in practice is you hand this to Mathematica or Python or whatever and say, here's this awful function. Plug in the numbers and put in T between 5,000 and 25,000 and make a plot for me. So that's what we're actually going to do here. I mean, it'd be, if you tried to do this on your calculator, it'd like, oh, okay, I'll do 5,000, now 5,100, now 5,200. Stop it, right? You could, but what's the matter with you? This is a job for Mathematica or something like that. And you know, if you look at it and you're like, wow, I can't look at that expression, right? If I put 2 copies of Saha in here and wrote this, I can't look at that and figure out what the plot's going to look like. I just see the plot and I'm like, oh, okay. And then you see if you can understand what the plot's telling you physically. And if you can see what it would look like just from looking at it, well, wow, you know, but anyway. So first we need the partition functions Z1 and Z2, because those show up in the Saha equation, right? We got Zi plus 1 over Zi. So here we're going to have Z2 over Z1. First we need the partition functions. Z1 and Z2. written with crossbars, of course, because ever since I took German in high school, I've written Z's with crossbars. How many of you just write Z's with crossbars anyway? Cool. Yep. Crossbar Z. Not that it's wrong not to have it there. All right, so H2, what's H2? What's that describe? The Roman numeral 2 is one more than the number of electrons that be removed, so this is hydrogen with one electron removed. Tell me, what is a hydrogen with one electron removed from it? It is it's a what? It's singly ionized, all right, but in other words, tell me, what is this thing? As a particle, what is this thing? It's just a bare proton. Yeah, you just pulled the electron off the proton. So H2 is a bare proton. Unless it's a deuterium nucleus, but let's not assume that. It's a bare proton, for which we don't have any internal degrees of freedom. There's no different arrangements of a proton. No internal degrees of freedom. So there's no degeneracy here. There's no different energy levels to worry about. And that says that Z2 is just 1, right? Z, remember that the partition function is multiplicity times e to the minus energy level minus ground state energy over kT. Well, there's no consideration of extra energy levels here for the proton. Internally, it's a ground state, that's all there is. And the multiplicity of that is 1. There's only one way to make a proton in a sense. So Z2 is just 1. Oh, I like that. That's easy. But what about Z1? What about for our neutral hydrogen atoms? Well, this is where we have this business. Remember last time we were talking about how, but the partition function that diverges because it's the sum of multiplicity, degeneracy, times e to the minus ground energy over the minus the ground state energy over kT. That blows up. So for Z1, but we have this idea of, but really high energy states don't really exist because they would be too big, the atom would be destroyed. So for Z1, note that the Boltzmann constant times 25,000 Kelvin, the upper end of our temperature range here. If you plug in the numbers, I gave you what K was in electron volts per Kelvin before, that's 2.15 electron volts. So that says that e to the minus E2 minus E1 over KT. And so I should probably remind you here that the way we defined the partition function was, so as an aside, the partition function was G1 plus, so the degeneracy of the ground state, plus the sum for every other state, J equals 2 to infinity, of the degeneracy of that state times e to the minus how high in energy that state is above the ground state over KT. So, and remember, it's G1 by itself here because E1 minus E1 is 0, and so e to the 0 is just 1. So if I made the partition function j equals 1 to infinity, well, I can just pull off the G1 because of the fact that the exponential gives 1 for the ground state. So for the hydrogen, we are adding up degeneracy times e to the minus energy above the ground state over kT. So let's look at the second term, in other words. We're looking at what is the contribution to the partition function for, here we say J equals 2, but for hydrogen J and N mean the same thing. Principal quantum number N equals 2. E to the minus E2 minus E1 over kT. Okay, so, and again, I want y'all to have this down. For hydrogen, what's E1?
13.6.
Minus 13.6 electron volts, because you take 0 to be ionized at infinity. So E1 is minus 13.6 electron volts. E2 is minus 13.6 electron volts over what? 2 squared, right? Because it's minus 13.6 eV over n squared, so minus 3.40 electron volts. So E2 minus E1 is,
Negative 10.8.
oh, it's minus 3.4 minus minus, right? Yeah, E2 is 10.2 electron volts above the ground state. Minus 3.4 minus minus 13.6 when you do E2 minus E1, right? So that's plus 10.2, right? Be sure you get that. Minus 3.4 minus minus 13.6, right? Because minus 3.4 is 10.2 larger than minus 13.6. So, what's that?
17.
What?
E to the 17 over kT.
No, just be E to the minus 10.2 EV, because that's E2 minus E1.
Oh, yeah.
Yeah. E to the minus 10.2 EV over 2.15 EV, because KT for $25,000, 25,000 Kelvin, right? So we're putting in 25,000 Kelvin there. So in other words, for the hottest temperature, what is the second term in the partition function? And then I lost where I was. Yeah. Gotta get back there. When you evaluate that, that's 0.00879. So the point is, for the partition function Z2 at 25,000 Kelvin, what's G1? What's the degeneracy of the ground state? That's what G1 represents. What's G1 for hydrogen, the degeneracy of the ground state? Say it loud, say it proud. It is 2, right? Because it's 2 because you got just the 1s orbital, the n equals 1 orbital, which has L equals m sub L equals 0, and the spin of the electron can be up or down. So there's only 2 ways. There are 2 ways to make the ground state in hydrogen. Electron spin up, electron spin down. There's only 1 orbital, the 1s orbital. So G1 is 2. And the contribution for n equals 2 at 25,000 Kelvin is 0.00879, right? So it's 2 plus 0.00879. In other words, when we've gotten to n equals 2, it's already much smaller than that first term right here. And the argument will be, okay, the really high level, the really high energy terms have been perturbed out of existence. Collisions won't let them exist. And the small values of n, which do contribute to the partition function, contribute way less than G sub 1 does. So the partition function is approximately just G1 or 2 is the argument that we're making here. So I'll complete the argument up here. I'll leave that, but I'll complete the argument up here. Right, because this is only going to get worse. At 5,000 Kelvin, this would be even bigger. So this is our worst case scenario, 25,000 Kelvin, the range of temperatures we're considering. You get even smaller values for smaller values of K, smaller values of T. So Z2 is equal to G1 plus G2 e to the minus E2 minus E1 over KT. Just for completeness, what would the next term be? I would write plus what? Just symbolically, what would I write for the next term? Right, this is the summation here. So the next term, put in J equals 3, becomes G3 e to the minus E3 minus E1 over, over KT plus dot, right? Well, so again, just for completeness, if I did include this term, what's G3 for hydrogen? In general, the hydrogen degeneracy is burn into the brain. For hydrogen, G sub n was, what was it?
2 sub 2 to the n.
2, not to the n, not 2 to the n, 2n squared, 2n squared, 2n squared. So what would G3 be? 18, right? 2, 3 squared is, that would be 18. And what would E3 be if I were going to evaluate this? E3 is minus 13.6 EV over what? 9, right? Over 9 over n squared, 3 squared. And I could keep going. G4 e to the minus E4 minus E1 over KT, et cetera, et cetera, et cetera. Now again, it would blow up if I also didn't account for the fact that once I get above n equals, I don't know, some value, those states aren't really there because that is so easily to strip that electron off that a collision will do so. So the partition function, we haven't included it. There's really an additional term that represents the probability that the state even exists, and that gets very small for large values of J. So what we're arguing here is that we can basically just say, okay, this is approximately just G1, which is equal to 2 over this range of temperatures. We're just neglecting all the higher terms because these exponentials are very small. So Z1 is, right, Z Roman numeral 1 is 1, and Z Roman numeral 2, okay. Nobody stop me. What is wrong with this right here? What should this really say right here? That should be a 1. It should be a 1 because I'm talking about the neutral hydrogen. So this is Z1 right there, the neutral hydrogen's partition function. Don't hesitate to show up the professor and say, Dr. Harmon, don't you, that's great when you do that. Yes?
Should it be divided by KT and G2?
Also, yes. Also, yes. Frickin' divide. Yes, thank you. So, why am I having so much trouble with that? God. Yeah, frickin' divide. Yeah. It's e to the minus E2 minus E1 over KT. Yes. Right. Very good. Yeah. Yeah, so then, and this is Z1 again, right? Oh no, this is general. Okay, so in other words, Z2 is 1 and Z1 Yeah, Z1 is 2 and Z2 is 1 in this case, right? Just interestingly enough. Okay. What questions do you have? So, inserting these values into the Saha equation, right, our Saha equation involves e to the minus chi I over kT, and for hydrogen then we're looking for, we'd be writing N2 over N1 is equal to 2, and then we would have the Z2 over blah Z1 for the partition function, blah, e to the minus chi, so ionization stage 0, because we're going from 0 to 1 for hydrogen, chi 1 over kT. That's what would show up if we wrote the whole Saha equation out. I've left out all the other stuff in there. So we need to put in what chi 1 is for hydrogen, the ionization energy going from the ground state of the neutral atom to the ground state of the ionized atom, which we would take to be, in other words, we've ionized the hydrogen atom and not given the electron any kinetic energy afterwards. That would be like the ground state, the lowest possible energy state of the ionized hydrogen, because you can knock an electron out of a hydrogen atom and the electron has kinetic energy afterwards if you give it enough energy. But let's say we've given it the very minimum amount. That's what we're looking for here, because we want to go from the ground state of stage I to the ground state of a stage I plus 1. Here that would be the ground state of the neutral hydrogen atom to the minimum possible energy of the ionized, no more electron hydrogen atom, meaning bare proton, bare electron, far from one another and not moving. How much energy does that take? What is the ionization energy from the ground state of hydrogen? Correct, 13.6 electron volts, because the ground state is at minus 13.6 eV. N equals infinity is 0 eV, right? Minus 13.6 over infinity squared is 0 eV. So the minimum energy to ionize hydrogen from the ground state is 13.6 eV. Give it any more than that and the electron is moving after you've ionized it, but give it just that amount and essentially you've dissociated the proton and the electron, and they're just like, okay, we'll just chill here. So chi sub 1 is 13.6 eV. Does that make sense? What questions do you have? 13.6 eV to ionize hydrogen from the ground state. I don't remember if I have the hydrogen. Yeah, there we go, right? So what we're saying here is that it's 13.6 eV. Here we've got the energies where it's relative to the ground state. N equals infinity is 13.6 EV above the ground state. Or the way a physicist would usually say it, this is 0, N equals infinity is 0, the ground state's minus 13.6 EV. Either way, the shift is 13.6 EV. That's what we're referring to here. The ionization energy for the ground state of hydrogen is 13.6 EV. What is it for N equals 2? What's the ionization energy for N equals 2 in hydrogen? If the electron's already in N equals 2, what's the minimum energy you need to give it to ionize it? 10.2 electron volts. What if it's in N equals 3? No, remember we're going backwards here, right? So in other words, it's like minus 1.51, because again, it's the difference between 13.6 and 12.1 that you have to give it. So here, it's, no, it's not 10.2. It's not 10.2. I fell for it too. I made the same mistake. Ugh, I quit. I have to hide behind the screen now. It's not 10.2. What is it actually? Not 2.4, it's 3.4. Yeah, I messed up, right. Yeah, it's 3.4 electron volts. 3.4 electron volts to ionize hydrogen from n equals 2, because there's only 3.4 electron volts to go from 10.2 eV above the ground state to 13.6 above the ground state. Or in physics speak, this would have been 0 and this would have been minus 3.40 right here. And this would be minus 1.51. So it's like 1.51 electron volts to ionize from n equals 3, and so on and so forth. But in the Saha equation, the ionization energy is always from the ground state to the ground state. So we want the 13.6 electron volts to show up here in the Saha equation. Yeah, I fell for it too. You all were so close to showing up your professor by pointing out that error. It would have been so glorious. Oh well. Oh well. Ha 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 ha. All right. So, with chi I, where were we? With chi I equals 13.6 electron volts, and plotting yields figure 8.8. In your book, I think it's still figure 8.8. I think I fixed that reference, which is a plot of N2 over N total for H from, this I'm really just restating what we've been getting at, from the Saha equation, because this is what we've been after, from the Saha equation with PE equals 20 newtons per square meter held constant artificially. So let's show the lovely plot, shall we? Yes, we shall. But first I should just show it to you all here. All right, here we go. Here it is. No, it isn't. It's the wrong slide. I forgot that was back here. Here it is. Ooh. Yeah, look at that. Look at that. Look at that. There it is. Notice that the x-axis is 5,000 to 25,000 Kelvin like we wanted to do here. Ooh, look at that, look at that. And we'll note a few things about it. And again, so you do this with Mathematica or whatever. You plug all that in and you say, okay, plot range, 5,000 Kelvin to 25,000 Kelvin. Do the math for me, Mathematica. And it says, no problem, because I'm Mathematica. And there's the result, and let's note some things. Note that, 50% ionization occurs at a temperature of about 9,600 Kelvin, roughly speaking. In other words, here's where it's 50-50 ionized versus unionized, ionized versus unionized. Occurs at T is about 9,600 Kelvin. That's suspiciously reminiscent of this, around 10,000 Kelvin is where you get the strongest hydrogen lines business, right? 5% ionization occurs at a temperature of about 8,300 Kelvin. And 95% ionization occurs at a temperature of about 11,300 Kelvin. All right, so if you just look in those ranges there. So in other words, for T much, much less than 10,000 Kelvin, H is essentially all neutral. And for T much, much greater than 10,000 Kelvin, H is essentially all ionized. And for T is 9,600 plus or minus 1,500 or so, we're in transition. H is going from being neutral to being ionized in that temperature range. And this is pretty characteristic, where you get this like neutral, 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 let's start ionizing, let's start ionizing, let's start ionizing, ionized, 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 ionized. There's this narrow range of temperatures that are like the ionization temperature for hydrogen under the density pressure conditions in a kind of typical stellar atmosphere. So, and for T is around 9,600 plus or minus 1,500 Kelvin-ish. H is transitioning between neutral and ionized. Transition between neutral and ionized. Yeah, so apparently, like, you know, the union busters work harder once the temperature gets hotter and just breaks up those hydrogen atoms. Question?
How do the stars with temperature over 10,000 Kelvin function then?
So, well, the idea is they don't care. They're perfectly happy to have the hydrogen be ionized. So in a hot stellar atmosphere, like a B star, for example, the hydrogen is ionized in the star's outer layers. And so free electrons are a significant source of opacity in such stars. But in cool stars, most of the hydrogen is neutral. Like for the sun, it's mostly neutral. But think in terms of going into the sun. So what's the sun's surface temperature, roughly speaking?
5,777.
Yeah, right. So we can say 5,800 Kelvin or even 6,000 Kelvin if we're feeling really sloppy. For the sun, characterize the hydrogen. Is it almost all neutral or almost all ionized or somewhere in between? Yeah, it's pretty much neutral. The sun has very little ionized hydrogen in its surface layers. Other more ionized species are the primary contributors of the free electrons in the sun's surface layers. And remember, that's why, as we alluded to last time, there's actually a fair amount of H minus of hydrogen that's picked up a second electron that was essentially donated by some easily ionized species. So in the sun's atmosphere, the hydrogen is essentially neutral for the most part. Most of it's in the ground state, not able to make Balmer lines, but there's a small fraction that are in n equals 2 able to make Balmer lines. As the temperature increases, if you go to a hotter star, as long as you're not ionizing everybody, you're also getting more and more folks in n equals 2, folks, hydrogen atoms are folks. Hey folks, in n equals 2, able to make Balmer lines. We're about to say that after the break more, but in other words, you got this interplay of, as the temperature gets higher, more and more of the neutral hydrogen are in N equals 2, able to make Balmer lines, but fewer and fewer of the atoms are neutral atoms to begin with for the hydrogen species. And so there's a happy medium, if you will, where Goldilocks gets to have the strongest hydrogen line she can, but dang it, if the star gets any hotter than that, there's just not hardly any hydrogen that is not ionized to begin with, and so you get weak lines again. That's the point here, is there's an interplay between Boltzmann and Saha. Boltzmann says higher temperatures are great for getting atoms into N equals 2 to make hydrogen Balmer spectral lines. But Saha says, yeah, but if you get the temperature too high, everybody gets ionized, and then you ain't getting no Balmer spectral lines, you losers. And so there's like this, this competition, if you will. Where was I going with this? Yeah, so sun, where was I going? Sun is mostly neutral hydrogen. Was I going to say something else? I don't know.
You were answering my question.
Oh yeah, what was your question? Oh yeah, right. Dive below the sun's surface. What's happening to the temperature?
It's increasing.
It's increasing. So get far enough below the surface, in the region where the temperature is getting to around 10,000 Kelvin, hydrogen is transitioning from being neutral higher than that to ionized lower than that. So there's a hydrogen ionization zone within the sun where the temperatures are right for hydrogen to be going from neutral to ionized, and then below that it's all essentially ionized. And ditto for helium. There's a first helium ionization zone where you're stripping off the first electron, and a second helium ionization zone where you're stripping off the second electron. Those are at temperatures of about 15,000 Kelvin and 40,000 Kelvin. And the ionization zones are crucial in driving stellar pulsations in many situations. Somebody should do a senior project on that. Yes. All right. It's break time. Excuse me. So I'm going to now officially write down the stuff that we were talking about just before break, which is now we can understand why the H Balmer line strength peaks at a temperature around, it turns out, 9,520 Kelvin. That H Balmer, in particular, line strength peaks for temperature of 9,520 Kelvin, and we've said it before. As T rises, the fraction of neutral hydrogen in N equals 2 rises. Right, that was this plot right here. As T rises, the fraction of, I'll underline, neutral H in N equals 2 rises. And as long as most H is neutral, the line strength rises with temperature. But, as T approaches 10,000 Kelvin, more and more H atoms become ionized and thus unable to make spectral line absorption. As T approaches, you can go past it too, of course. As T approaches 10,000 Kelvin, more and more H becomes ionized. More and more H atoms become ionized. And unable to produce absorption lines. And that was the big insight of Cecilia Payne combining the Boltzmann and Saha equations. Absorption lines. Absorption lines. And so, you know, that's all that was like, you know, summarized by this whole Balmer thermometer stuff that we first did kind of qualitatively talked about, is that, you know, but when Goldilocks goes to a star that's well below 10,000 Kelvin, her problem with her desire to get strong Balmer lines is, yeah, most of the atoms are neutral, able to make spectral lines, but also very, very, very few of them are in n equals 2, able to make Balmer lines. And if you go to a very hot star, they're just straight up ionized, and then you got no electron to do any absorption, and so you don't get strong lines. Not nothing, it's not 100% ionized, but getting close. And then for around 10,000 Kelvin, you know, I'd kind of modify this, say, for 10,000 Kelvin, a still very tiny but largest possible number of H atoms are neutral and also excited to n equals 2, able to form Balmer absorption lines. But it's always tiny. There is always, no matter what, very few of the H atoms that are able to produce the Balmer absorption lines. But around, well, really 95-20 is when you've maximized the situation. And so if you combine, and we'll be more specific in a moment, if you then combine these concepts, combine the Boltzmann equation and Saha equations, you can make a plot of the fraction of hydrogen atoms that are in little n equals 2. Right, the number that are in little n equals 2, they're neutral, and they've got an electron just saying, oh, please, please, please come Balmer photon wavelength along so I can absorb it and contribute to a Balmer absorption line. This is my wee life's goal, fulfillment, and then it drops back down again, but whatever. Divided by the total number of hydrogen atoms. You combine them, and you get a plot that looks like this, which is saying, ooh, bad if you're well below 10,000 Kelvin, ooh, bad if you're well above 10,000 Kelvin, and there's a peak that's a little below 10,000 Kelvin, where you optimize the situation if your life's goal is to have strong hydrogen lines. And whose life goal isn't to have strong hydrogen lines? I mean, I ask you, right? So, what questions do you have? We'll be a little more quantitative in just a second here. I'm going to do it. Yes? Uh-huh. Oh, you're writing. Oh, okay. Got it. Okay. We can allow that. So, quantitatively, we have N2 over N total. So neutral atoms in N equals 2. Neutral H with N equals 2, little n equals 2. So that capital N means, you know, when we're writing this here, this is supposed to be the total number of the atoms in your box, so to speak. These could also be number densities. You could divide through by the volume of the box and say the number density of hydrogen with an electron in N equals 2 over the number density of all hydrogen atoms put together is equal to, we could say that it's N2 over the total number of ionized hydrogen atoms times, neutral, God, reverse it again. N1 is neutral hydrogen, so the fraction of neutral atoms that are in N equals 2 times the total fraction out of all the total atoms that are neutral. So just write that as N2 over N, N2 over N Roman numeral 1 times N Roman numeral 1 over N total. And this will be approximately equal to N2 over N1 plus N2, not Roman numerals yet. And that's because, so really, the number of neutral atoms is N1 plus N2 plus N3 plus N4. In other words, how many neutral atoms are in the ground state, plus how many are in N equals 2, plus how many are in N equals 3, plus how many are in N equals 4. So this should really be the sum all the way up to N sub infinity here. But at these kinds of temperature ranges, there's very few up in N equals 3. Almost everybody's in the ground state. A few of them are excited to N equals 2. Even fewer are in N equals 3 or N equals 4 and so on and so forth. So in other words, we're approximating that of the neutral atoms, they're almost all either in the ground state or in the first excited state. And everybody else is, we don't care about you. So this is saying almost all at these temperatures, neutral H are in little n equals 1 or little n equals 2, because it gets harder and harder to excite them to higher values than that, times, well, remember that the total number of hydrogen atoms in terms of ionization is N1 plus M2. Shh, I'm not including H minus here. Shh, shh, leave me alone. N1 plus N2 equals, and if it were pure hydrogen, I don't have to worry about H minus. No electron's going to join a neutral hydrogen atom when it could join a proton instead. And so now, you know, we just love making ratios that the Saha or the Boltzmann equation can actually tell us. And so we'll divide both numerator and denominator in the first term by n sub 1, not a Roman numeral, and the numerator and the denominator of the second term by n sub Roman numeral 1 to turn it into N2 over N1 over 1 plus N2 over N1, not Roman numerals, times N1 over N, oh no, I'm doing it, yeah, I'm just going to leave it like that, sorry. I'm going to divide now both sides, no I'm not going to, I'm going to divide by N1 in the numerator and the denominator over here, so N1 over N1 is 1, and N1 plus N2 over N1 is 1 plus N2 over N1. And just to see if you're following, how would I calculate N2 over N1? I would use the equation, where is It's not Roman numerals. I'm not looking at ionization here. I'm just looking at neutral atoms. So I would use the equation, the not Saha, but Boltzmann equation. I would use the Boltzmann equation. The Boltzmann equation can also apply to ionized species, but we're talking about hydrogen here, and so we're only interested in neutral hydrogen. If we're talking about helium, you could use the Boltzmann equation for different energy levels of singly ionized helium, for example, but here I'm talking about hydrogen. From the Boltzmann equation, thank you very much, Ludwig. From Boltzmann, both copies there, and n Roman numeral 2 over n Roman numeral 1. Why that comes from equation where is Saha. Yes, from Saha. Thank you, Megnan. And so then we put those all together, and it gives us that figure right there. Result, no, sorry, it's result figure 8.9. Glorious figure 8.9. Oh, not this. The arrows went under that. They're pointing over here. It's that right there. And so, you know, now that Willow and Kale, you've enjoyed this view, you've seen it, look quickly, I'm about to turn away from it, or just pause the video, and then we can come over here. It'd be funny if they paused it right at that moment, and then they kept going, and they had no idea that, you know, I had paused it myself, so to speak. So this, the peak from that calculation where we did this all for the pure hydrogen and all that is at T is around 9,900 K for the pure H, constant electron pressure of 20 newtons per meter squared, per square meter. But that agrees well with the observations, right? In other words, we made some approximations, and it says 9,900 Kelvin. Okay, the observations say 9,520 Kelvin. Good enough, right? We made some approximations, so we're confident with that we understand what's going on here. I'll say, and that agrees well with the observations. Which means, in other words, the observations are strongest lines for T is 9,520 Kelvin. So, good enough, good enough. We pat ourselves on the back here, good enough. What questions do you have? So now we've put details behind our qualitative before description of Goldilocks and the 3 stars. Now Goldilocks did some math and made some plots with Mathematica. And in the future, she won't even bother with those hot and cold stars because she did the calculations and she can see she needs to go to stars. You know, best would be around 9,520 Kelvin. But her calculation said 9,900 Kelvin. She'd have plenty of delicious Böhmerlein feast there too, so it'd be fine. Okay? All right. Now we're going to change gears a bit. How many of you have already taken, I forget, StatMech? And how many have not taken StatMech yet? Oh, cool, all of you. Oh, y'all are gonna know so much going in already. You're gonna be like, yeah, I've seen all this, and thank you, Dr. Trees, or maybe Dr. Ding, for showing us the details like Dr. Harmon promised you would, but we've already seen this before, so we already know the whats and some of the intuitive whys, and now we're just so ready for this. It's gonna be great, it's gonna be great. But let's look now at the Maxwell-Boltzmann distribution of speed. So that's for classical thermodynamics. You want to know, in an ideal gas, what fraction of atoms, if you will, or molecules or whatever, are moving at different speeds. We know in general, the higher the temperature, the higher the average kinetic energy of all the atoms, so therefore the faster they're moving. Can we be more specific? Just like Wien's law says, the higher the temperature, the shorter the wavelength of peak emission, so that the color gets bluer and bluer. But then you can also say, but here's the Planck function, which gives the details of how intensity varies with wavelength. We're going to do the same thing for the atoms in a gas. We're going to give the details of how, what fraction of molecules or atoms are moving at what speed as a function of temperature. The Maxwell-Boltzmann distribution. Can I erase this? Okay. The Maxwell-Boltzmann distribution, one of the most important results in statistical mechanics, named after two of the greats. After all, you ever hear of James Clerk Maxwell? Yeah, James Clerk Maxwell didn't just do E and M, the Maxwell-Boltzmann distribution. Of speeds in an ideal gas. In thermal equilibrium, if we really want to be complete here. In thermal equilibrium. Any individual atom or molecule is bumping into other ones, changing its speed constantly. So this is not that an individual atom sticks with some particular speed. It's that in thermal equilibrium, the number of atoms that are being bumped into any particular speed and bumped out of that speed are the same, so that the overall fraction of atoms in any given little narrow range of speeds stays constant, except for statistical fluctuations. There's always statistical fluctuations. So, it looks like this. Here's the formula. N sub V dV is equal to capital N times little m over 2 pi kt to the 3/2 power. If you notice, there's a certain affection for like things that kind of look like that, to the 3/2 power, times, oh look, we're going to get a Boltzmann factor, e to the minus mv squared over 2 kt times 4 pi v squared dv. And you might be, well, why did you write 4 pi v squared separately? Why not put it inside the brackets there or whatever? And we'll say why in just a minute here. Ooh, there it is. There's what the plot looks like. And have you noticed, by the way, there's a real tendency for things to look like this in thermodynamics, right? It's not exactly the same as the Planck function, but again, we've got the kind of like rises to a peak and then there's a tail, so to speak. Here's the Maxwell-Boltzmann distribution for hydrogen atoms at a temperature of 10,000 Kelvin. VMP is the most probable speed, meaning it's where the peak is of the distribution. And that's at 1.29 times 10 to the fourth meters per second. So in other words, that would be what, 12.9 kilometers per second, versus VRMS, root mean squared, the square root of the mean of the squared speed is a bit higher, 1.57 times 10 to the 4 meters per second, so like 15.7 kilometers per second. This is for 10,000 Kelvin, that's pretty toasty. But even for the molecules in this room, the typical speeds are thousands of kilometers an hour, thousands of miles an hour. So thermal motions, sometimes you may not appreciate that. Your atoms or molecules are moving thousands of miles an hour, bumping into one another. So think of a car, right? Car drives down the highway. What's a typical highway speed in either miles or kilometers per hour? Yeah, like maybe 70 miles an hour. Okay, if you called it 62 miles an hour, that would be 100 kilometers an hour, kind of typical speeds. Versus the thermal speeds of those iron and other atoms is thousands of miles an hour. So thermal kinetic energy is still kinetic energy. It's, in other words, we can talk about the bulk kinetic energy of the car, the 1/2 mv squared, where v represents the center of mass speed. And that's going to be like 1/2 the mass of the car times 100 kilometers an hour squared. Okay, turn it into meters if you want joules, right? Versus the thermal kinetic energy, what's bigger? And is it a lot or a little bigger, the thermal kinetic energy or the bulk kinetic energy of that car driving down the highway? Which one's bigger? How fast are the molecules jiggling around in the car, did I say? I mean, you're just telling you to trust me. It's like thousands of miles an hour, right? That's a lot more than 60 miles an hour. Most of the kinetic energy of a car is thermal kinetic energy. You too, right? You can run as fast as you like. Usain Bolt, most of his kinetic energy was thermal kinetic energy, right? Which is what would show up if we were doing, not that it would apply virial theorem there, but right? So just remember, like when you're doing this virial theorem stuff, it's almost all thermal kinetic energy that we're talking about there for like a cloud of gas or something like that. So that's the thing, is that the microscopic thermal motion, except for very low temperatures, is going to be quite large compared to the bulk kinetic energy. So here's a plot. The plot, notice, was in terms of little nv over little n, and it's the same kind of idea here. In other words, I could write capital NV over capital N, which would mean the total number of atoms divided by, or the total number of atoms with speeds between v and v plus dv is n sub v dv, and I could divide by the total number of atoms, or I could divide the whole thing by the volume and turn it into number densities instead. It doesn't matter. This could be little n v dv, little n to be per unit volume, or just, if I have a box, the total number of atoms in both cases. So here the label was little nv over n, but you could just as well have been capital NV over capital N, because the fraction is the same for some little region with a certain number density multiplied by the volume. That's the total number of atoms in that region. So this is like F lambda, right? Whereas F lambda d lambda is how many watts per square meter in a little range of wavelengths, lambda to lambda plus d lambda. This is that same kind of thing. N sub v dv, what would I say here? Where n is the total number of particles, n is the total number of particles, and n sub v dv is number of particles with speeds between v and v plus dv. So again, this is one of these continuous distribution things where, okay, it's actually discrete individual particles, but we're treating it like a continuous function. We're treating it as though you could say there's 0.747 particles in this little narrow range of speeds. We're treating it as a continuous distribution. And if we make the plot, we could make n sub v over n if we like, just divide through by n. So there's that function, looks something like this. The idea is here's speed v plus dv. We'll be bad people and label the axis v and then also call this v, which is, okay, shh, don't tell Dr. Nunemacher I did that. And so I'll just leave it as n sub v. So this overall factor of n and everything. So tell me geometrically, what is n sub v dv? In my picture here, what is n sub v dv? Geometrically. So n sub v dv is the number of particles with speeds between v and v plus dv. Here's the value of n sub v. Here is v to v plus dv. So in other words, this little width right here, that's width dv. What is n sub v times dv geometrically? It's that little area right there. Yes, it's that little area, right? Area n sub v dv. So, and again, this is again, that subscript v really means n as a function of v, just like f sub lambda meant f as a function of lambda. N sub v is our funny notation, n as a function of v. N sub v dv equals number of particles with v in this cute little range. In that cute little range. Can I erase this part down here on this side? Anybody stopping me? Okay. So tell me, if I did the following integral, what would I get? If I add up n sub v dv from 0 to infinity, I'd be adding up how many particles are in each little narrow range of v's. And if I added up how many particles are in each little narrow range of v's, what would the result be? It would be the total area under the curve, which would be the total number of particles, right? So in other words, that integral is n, the total number of particles. So one way to look at this is the normalization factor that makes that work. Actually, right. Okay. And we can understand how this arises as follows. We can understand what this expression represents as follows. If you'll take my word for it, like before, that a Boltzmann factor is the probability that something will have a certain energy. We did that before when we were talking about like the Boltzmann equation, right? We said e to the minus an energy over kt is proportional to the property that something will have that energy. And you have to get that from StatMech. But if you take my word for it, waving the hands, chicken feet, if you take my word for that, we can actually figure out where this comes from. So we can understand how this arises as follows. So let's go into velocity space. In other words, so how many of you had mechanics already? 310, right? You remember talking about momentum space, right? So a particle is characterized by, it lives in 6 dimensions, so to speak. X, Y, Z, Px, Py, Pz. So you can talk about momentum space. You could talk about how many particles are in a little range of momentum space. Let's just do velocity space instead. So in other words, let's go into velocity space. Vx, Vy, Vz. Here's a little cube in velocity space that is representing particles whose velocity vectors are very near to that vector right there that points to the center of the cube, v. And we could say that the probability, by the way, I love this kind of thing. I just do. The probability that the velocity vector v of a particle lies in a little volume, a cute little volume. They should be cute. I mean, they can be ugly too, but I prefer them cute. A cute little volume, and we'll call that D3V. Have you seen that kind of notation before? Like D3 something means like dx, dy, dz if we're in position space. So D3V, a little volume, in other words, this will have widths of dvx, dvy, and dvz in velocity space. D3V looks kind of like d cubed v, if you will. It's funny notation, but whatever. Equals dvx, dvy, dvz, a little volume, a little rectangular volume of dimensions dvx, dvy, dvz in velocity space, should be, again, if you just take my word for it, that a Boltzmann factor gives such a probability, should be proportional to the Boltzmann factor they show up whether we're talking about energy levels in atoms or kinetic energies of particles, e to the minus kinetic energy over kT. Because remember, kT has units of energy. It's the characteristic thermal energy, kind of a typical energy for particles to have at temperature T. So e to the minus kinetic energy over kT, or in other words, the probability density for being near velocity vector v times the little volume in velocity space should be proportional to so the probability any given particle is in this cute little volume of velocity space should be proportional to, there should be some factors that allow normalization. There's the proportion fish, something times, proportional to e to the minus, what's the kinetic energy? If the mass of the particle is m and its speed is v, its kinetic energy is, channel your physics 110 or even your high school physics, why the ke of a particle of mass m and it's moving at speed v, why that would be 1/2 mv squared, right? So it'll be 1/2 mv squared over kT, also known as mv squared over kt. 2kt. E to the minus mv squared over 2. Right? Boltzmann factor. Boltzmann factor. Insert angelic choir. Right? Boltzmann factor. That's if we want it in that cute little cube. But what if what if all we care about is not the three components, Vx, Vy, Vz? What if all we care about is how fast it's moving and not what direction it's moving? Because it should be isotropic. It should be in a gas that is just as probable to find the particle moving at some speed this away as it is this away as it is this away. That shouldn't matter. It should be spherically symmetric in velocity space. So we should be able to just consider spherical shells in velocity space. Can I erase this stuff? I should probably, yeah, I'll just leave that there for now, okay? If all we care, actually, can I erase that stuff? Or are you still, can this go? Can this go? Okay, it's gonna go. Bye. Bye, nice knowing you, bye. Bye, bye. Bye, bye. Bye-bye. If all we care about is the magnitude of V, then we can consider a spherical shell in velocity space. And you're like, oh my God, I've seen so many spherical shells in E and M right now that I just like, oh, another one. It's like different classes can be related to one another. Weird. We can consider, it's like there's unified concepts in physics, imagine. We can consider, and math, we can consider a spherical shell in velocity space. So, remembering that I'd better draw the shell and then put the origin in the center of it, because I am not Dr. Bradley Trees. There's my spherical shell. So it's, okay, it's two circles. You know, it's a shell, okay? So here's our Vx, Vy, Vz there. Vx axis, Vy axis, Vz axis, but let's use spherical coordinates in velocity space. Ain't nobody stopping me. So our shell has radius V, and it has thickness dV. So you tell me the volume of that shell is d3v equals, it's a spherical shell. If you're just in regular space, sphere of radius r, spherical shell of radius r, thickness dr. Oh my God, please tell me, what is its volume?
4 pi r squared dr.
Ah, yes, it is 4 pi r squared dr, right? Surface area, 4 pi r squared times thickness dr is its volume. But we're in velocity space, so the radius is v and the thickness is dv. So its volume is 4 pi v squared d, v squared d, what's its thickness? Instead of 4 pi r squared dr, it'll be 4 pi v squared d, v, dv, dv. 4 pi v squared dv is the thickness, is the volume of that shell in velocity space. Now it's got funny units because velocity is meters per second instead of meters, right? So this is going to be meters cubed per second cubed is the units here because of weirdness, but that's all right. 4 pi v squared dv. And so n sub v dv should be then equal to the total number of atoms of all velocities times the probability that any given atom is in that little volume of velocity space. That'll be P of v dv. That'll be the probability that that atom is in that volume of velocity space times the total number of atoms. The probability any given one atom is in that spherical shell velocity space times the total number of atoms will be how many atoms are in that spherical shell in velocity space. How many of them have that range of speeds between v and v plus dv, right? This is probability a given atom is in the shell. That's the P of V D3V. Probability a given atom is in the shell times total number of atoms equals number of atoms in the shell. And when I, when I say in the shell, I don't mean literally, this isn't physical space, it's velocity space. It's the number of atoms whose velocities live in that little shell in velocity space. So n sub v dv then is going to be equal to what I just said over there, n times p of v d3v, but as we've argued, that's going to be proportional to, we'll have n times Boltzmann factor, e to the minus kinetic energy over kT, e to the minus mv squared over 2 kT, but wait, d3v is 4 pi v squared dv. 4 pi v squared dv, and voila, there it is. There it is. Insert more angelic voices. Oh, it's so beautiful. It's so beautiful. It's so beautiful. So that must just be the normalization factor in the proportionality. That's just what you need. If you did the rest of the integral, you'd be short by this of what you needed to make the integral be n, in other words. It's the normalization, like in quantum mechanics, you need a factor in front of psi to make psi star psi integrate to 1. Same deal. This is the normalization factor. That piece is the normalization factor. From this, and actually doing the integral, we can deduce that factor of m over 2 pi k t to the 3/2 is a normalization factor that makes the integral from 0 to infinity of n sub v dv actually be equal to the total number of particles. Or put another way, it makes the rest of this stuff integrate to 1. So it's very similar to a quantum mechanics normalization factor, coefficient, if you will. Excuse me. And I guess now it's basically time to stop, and then next time we'll talk about the significance of V most probable and VRMS, and that's how we get this idea that in thermal equilibrium, the total thermokinetic energy for a monatomic gas is 3/2 times the number of particles times kT, because the VRMS speed makes that work out, essentially. It makes the average kinetic energy per particle equal to 3/2 kT, for example. I think it's 3/2 kT if I'm not mistaken, et cetera, et cetera, et cetera. It's glorious. So anyway, time to go, unless you got any burning questions that make you want to not leave. Okay, ask a burning question. If the rest of you want to leave, losers, go ahead. Yes, question.
When is our next one?
I'm still deciding that, because dang it, next week is break. How annoying.
Indeed.
I know. So I'm thinking, should I give him like 1 or 2 problems for next week, or, yeah. What do you, I mean, you probably you're burning to apply this and get 1 or 2 problems for next week. Or maybe you just want to laze around and learn more from a homework that's bigger the following week. I'm getting, what's that?
I'll take the smaller one.
You'll take this, interesting,
Hopefully prove all these.
Yeah. Oh, I'm getting conflict here. It means I have to just decide. Yes.
Could you just make it a big homework, but assign it at the beginning of break and then make it due at the normal time the next week, so then we have the whole time to kind of.
So in other words, if you're dedicated, you could like do a first part of it early and then yeah, probably do that. Yeah. Okay. I mean, yeah, but it would be like, the Thursday after break.
Oh, okay.
Right.
But the week we come back, there are 2 big exams.
Yeah, we
Including the exam.
Oh, stop it. Well, I still have to, I can't let you just drift. So you might just, if you're bored during the break, right? One of your exams, like what?
Could it be due, could the work be due on Friday or something?
I can make it due on Friday, yes, but then you won't even look at it. If you're just not going to look, okay, I'm going to make it due on Friday, and you're going to exhibit such great time management skills that you're going to be slowly doing this homework all that time, because it's so important that you're not going to try to do it all Thursday night after your exam and get nothing out of it, because you all have great time management skills. All right, so it's going to be due Friday then, okay, and this is, okay,
How
all
many
right.
problems would be based on what you would have studied by Wednesday?
Probably about 45 problems. No, 45. Yeah, I don't know.
To die.
Yeah, and then it'll make the rest of the semester so easy on me, right? Yes.
I have an exam on Friday too. Just say
Oh, for God's sake.
Which class has an exam on Friday?
abstract.
Abstract algebra.